Hi, welcome to my presentation. My name is William Ho. The topic of my research from the past few months here is signal processing from a pulse generator. And this project was made possible with the help of my mentor, Dr. Manila Rondo, and the Department of Physics. And now, the main object of interest here is an antimatter particle called the positron. It has the same mass as an electron, but it has a positive charge instead of a negative charge. And the reason why we're interested in these positrons comes from the question, where do these positrons come from within our Milky Way galaxy? This is because previous observations have shown that there is an unknown source of positrons coming mostly from the center of our galaxy, the galactic bulge, and a little outside that. We don't exactly know how these positrons are created, and so we're just focused on getting a clearer picture of where they're coming from. But seeing these particles are not that straightforward. We don't see the physical particles, but when a positron and electron collide and annihilate, they convert their mass into these 511 keV photons, and it's these gamma rays that we see and detect. Now, with these gamma rays, we can't see them on the surface of the Earth that well because the protective atmosphere tends to absorb photons of these energies. So we'd have to send a detector into orbit in order to detect these gamma rays. And the most current sensitive mapping of these gamma rays was done by the International Gamma Ray Astrophysics Laboratory, also known as Integral, launched by the European Space Agency almost 2 decades ago. And the goal of my research group is to assemble a detector to surpass Integral. And such a detector would be smaller of the CubeSat and SmallSat class, and a CubeSat would just be an oversized Rubik's Cube that you can stack together. And much of the characterization of the performance of our proposed detector has been done with simulations in the past, remote research due to COVID. And a big goal this summer would be to obtain data from the physical detector that we have in our lab, which is great. So when when one of our detector is a high purity germanium detector because it provides the best energy resolution. When a photon hits the high purity germanium crystal, we see it as a voltage pulse, like the one shown in this graph. And in the lab, we would use radioactive sources in order to create gamma rays so that we can see these pulses. And this is the detector that we have in the lab that we would have used for our data. And I say would because very, very unfortunately, on the first day of my summer research fellowship, the cryostat that cooled our detector broke. So we couldn't use it while it was being sent away to be fixed. So, my lab setup instead of this summer was this. While the detector, while the crystal itself was unusable, our other equipment was working. So we can instead use a pulse generator like this one to create synthetic voltage pulses. And with these voltage pulses, we can plug them into an oscilloscope or a digitizer so that we can observe these pulses. And with a digitizer, we can plug it into a computer and record these pulses. And with the recorded data, we can plot each pulse as such. And but our main interest is the height of these pulses. The energy of the photons is proportional to the voltage height. So we can calculate the height of these pulses by taking the difference of the peaks of these pulses with the baseline. However, as we see here, each voltage trace is not perfect. We can see that there's noise here in the form of these spikes, and they can interfere with calculating the maximum of each pulse, the peak of each pulse. So it can mess with our pulse height data. So in our case, we strongly believe that it's the result of our pulse generator causing these spikes, and we can fix it by simply replacing it. But we realize that when connecting it to a real detector, the digitizer to the real detector, we need to be prepared for any noise that can show up for any reason. So it would be best to try and filter out these spikes using techniques from signal processing. And well, coming into this summer research experience, I had never done signal processing, and I was still very new to Python. So as I'm learning along the way, I found three potential filters to apply to our data, like these three. And our goal was to find the filter that works the best at removing these spikes while distorting our data the least. So on the left here, the low pass filter works by taking the Fourier transform and finding a point to cut off all the higher frequencies. And and the goal of that is to just take practically just eliminate the high frequency spikes that exist on the pulses. And this is not very effective, as we can see, because the overall pulse is not periodic, nor are the spikes. And our second one, in the middle, the filter in the middle, is the moving average filter, which we take multiple windows, average the values inside, and replace each window with the average value. Of course, in the graph's case, the windows are much smaller and greater in number, but that's what we have here. And to the right, we have the same thing going on, but instead of taking the average, we take the median. And out of these three filters, it seems that the median filter works the best, but we can't just go off based on looks. We have to find a way to quantitatively say which filter is the best. So I developed a test, a way of scoring which filter works the best by picking out a bunch of pulses where the spikes aren't too close to the tip of the peak. So I can calculate the peak of the whole pulse by manually selecting a window to calculate the maximum from. And of course, again, taking the difference with the baseline. And by summing up the absolute value of the difference of heights calculated in each filter and comparing it with the true value, I can provide a score here for each filter. And then as shown here, we see that once again, as we first suspected, the median filter works the best. But in hindsight, doing this test, a better scoring system would be by summing up the square of the differences in pulse heights. But in our case, it doesn't even matter because the median filter is the only filter capable of fully removing the spikes. So, which means that for spikes that are on or very near the peak of the pulses, we would not run into the same trouble of calculating the wrong pulse heights. So what's the point of going through all this trouble again? When we get our detector back up and running, we are further prepared to read out the data that it gives us. So instead of focusing on reading the data and filtering out the data from that detector, we can focus more on the performance of the detector and once again focusing on the bigger picture, taking a step closer to seeing our own galaxy with a better pair of glasses. And doing all this, we hope to learn something more about our home in the universe. So thank you for listening in and taking a moment of your time to learn a little bit more about what we're currently trying to learn about our vast universe.